Hello everyone, welcome to another video on my channel. So in today's video we'll be looking at the big O notation. So a lot of us have been asking me to make a video explaining the concept of the big O notation and time complexities of algorithms. And this video is also very similar to what we are doing in the Ace in the Code interview series. So this video will aid your understanding of data structures and the runtime of most algorithms will be implementing in most data structure. So stick to the end of this video and pay rapt attention. Don't forget to ding that subscribe button and like the video, and also share with your friends. So in this channel, what we basically do is simplify hard computer concepts and software engineering and development practices to just simplify it for both beginners and intermediates to understand these concepts better. So we start off with defining what a time complexity is and what the big O notation actually is. So a time complexity is the total amount of computer time it takes for an algorithm to run. So basically in your web browser, or sometimes if you're a web developer, you check the dev tools, you can see the network time, you can see the load speed of the page and something like that. So the time complexity is more like the amount of computer time it takes for an algorithm to execute its code, to execute its function. So the big O notation, on the other hand, is more like the metric system for measuring the time complexities. So the big O notation groups algorithms with similar time complexity classes together. So the big O notation, just like meter for distance, grams for weight, liters for liquid, the big O notation is for computer time speed. Actually, the big O notation is a mathematical concept, but is a mathematical concept used to check is it the nature of functions in mathematics. So it was introduced into the computer science world because even the computer science was built strongly on mathematics. So next up, we'll be looking at the different time complexity classes and their big O notation. So the first complexity we'll be looking at is the constant time complexity, denoted with a big O of 1. So this is one of the most common time complexity. So many functions we write or algorithms we write run on this time complexity. So what is a constant time complexity? For a function to be called to be denoted with a big O of 1, its time complexity to be denoted with a big O of 1. It means that the time execution of the algorithm is not variable, meaning that it doesn't change, it is fixed no matter the input size given to the algorithm or to the function. So it is the fastest time complexity because of its fixed and it's not changed, it's invariable. That's why it's called the constant time complexity. So an example of this is like a function that takes in two inputs and adds them together. That's an example of a function with a constant time complexity. So we are looking at the linear time complexity, and is another common time complexity. We find it when we are working with loops and stuffs of that nature. So it's noted with a big O of n. So it is a time complexity in which the time execution of the algorithm is dependent on the size of the input. So you see this when you're like traversing through an array, like iterating through an array. So as you're iterating, the time execution of that algorithm is going to depend on the size of that array. So that's what linear time complexities are all about. So if an algorithm has a linear time complexity, it means that the size of the input is going to determine when it's going to finish running, unlike the constant time complexity that doesn't care whether the input is big or small. It just executes what it executes because it's not dependent on the input size. So the logarithmic time complexity, which is denoted with the big O of log n. So this is a time complexity in which the time execution or the runtime of the algorithm is dependent on the halving of the n input size. So unlike the linear time complexity where every input size, every n inputs is going to affect the runtime of the algorithm, the logarithmic time complexities, algorithms with this complexity, they don't really depend entirely on the input size, rather they depend on half of the input size. Like in binary search algorithms, you can easily find this time complexity, this logarithmic time complexity, because you're only going to get to search half of the array input size. So if there were 10 elements in the array, you're going to only search 5 of them because it's going to be half the two. So that's what the logarithmic time complexity is about, and it's the closest to the constant time complexity, so it's the second fastest time complexity. So raw algorithms with this time complexity are actually really fast, at least faster than the linear time complexity and the quadratic time complexity. Okay, so this is the quadratic time complexity denoted with the big O of n raised to power 2. So this is a time complexity. For an algorithm to have this particular time complexity, it means that that algorithm is, the time execution of that algorithm is dependent on the square of the size of the input. So you can easily see this in nested loops. So assuming you're iterating through a matrix, these two-dimensional arrays, you will easily encounter this quadratic time complexity, because you're going to both iterate through the first dimension of the array, then you're going to still iterate through the second dimension of it. That squaring it up. So that's why the time execution of the algorithm is dependent of the square of the size of the input, which is n. So next off, we are just moving from crazy to crazier time complexity. So the next one is going to be a much slower one, and we'll keep on going down the line till we get to from the common to the uncommon time complexities in programming. Okay, so this is the quadratic time complexity denoted with the big O of n raised to power 2. So this is a time complexity. For an algorithm to have this particular time complexity, it means that that algorithm is, the time execution of that algorithm is dependent on the square of the size of the input. So you can easily see this in nested loops. So assuming you're iterating through a matrix, these two-dimensional arrays, you will easily encounter this quadratic time complexity, because you're going to both iterate through the first dimension of the array, then you're going to still iterate through the second dimension of it. That squaring it up. So that's why the time execution of the algorithm is dependent of the square of the size of the input, which is n. So next off, we are just moving from crazy to crazier time complexity. So the next one is going to be a much slower one, and we'll keep on going down the line till we get to from the common to the uncommon time complexities in programming. So this is the exponential time complexity. So it's denoted with a big O of 2 raised to the power of n. So it's way much slower than the quadratic time complexity. And if you look at it, it is exponentially slower than the quadratic time complexity. So in this time complexity, the time execution of the algorithm is dependent on the double growth rate of each input, which of each n input, meaning that each input is going to be doubling because 2 is going to be raised to the power of the size of the input. So this algorithm normally occurs in recursions. Like if you're doing something like the Fibonacci sequence or something like that, Fibonacci algorithm, you can find this kind of time complexity in it. So the bigger the inputs, the longer you wait for the operation to be successfully executed. So that's why it's called the exponential time complexity. And if you look at it in proportionality to the quadratic time complexity, you see a very huge time gap in it. So we'll be looking at some other uncommon time complexities from this clip to the next one. So we are looking at the factorial time complexity, denoted with the big O of n factorial. So this particular time complexity is pretty uncommon and not that popular, and is not really talked about because we don't normally encounter it, though we encounter it sometimes, like hackers encounter it normally. So it's a time complexity in which the time execution of the algorithm is dependent on the factorial of input n size. So the runtime of this algorithm is totally dependent on the factorial of the input size. So you normally encounter these factorial time complexities in algorithms such as trial and error algorithms, like brute force algorithms, where you're going to try a lot of factors of the input size. So in fact, like you're going to, like in a brute force attack, you have a lot of passwords and have a lot of words to check and combinations to check. So one may fail, you go to the next one, keep on going to them, going. That way you're creating the algorithm is said to have a factorial time complexity, because each input will have, you have to check the factorial of each input, so thereby increasing the runtime and making it much slower. So try to avoid your algorithms having this time complexity as much as possible. I think the exponential time complexity does better than this, or they are just almost the same. They will have almost the same runtime results. So, but they have a pretty bad performance. So, your algorithm should normally have this time complexity when you're working with a smaller input size, because if you're going to work with a large input size, it's going to take you forever for your algorithm to run. So we've come to the end of this video. Thanks for watching. Don't forget to like, subscribe and share. And if you haven't checked out on my series, the Acing the Coding interview series, where I provide every resource you need for you to ace your coding interview, please do check it out. It's very helpful and resourceful for anyone hoping to land their big tech job. So thanks for watching once again, and anticipate the new videos which I'll be releasing soon. Bye.